All right, let's get started. Hope you guys had a good weekend. So we're going to start a new unit today on the topic of classification, which is going to be a new task for us. We've been working on regression this whole time. And the data set that we're going to use in the demo is about diagnosing breast cancer. So my understanding of the way that this is usually done is that there's some sort of tissue sample taken and it is stained and looked at in a microscope by a person, an expert who's used to looking at these cells. And what they do is they make, they basically quantify various things about what they see, like the thickness of clumps, the uniformity of cell size, uniformity of cell shape, and so on. They assign numerical values to each of these, and then that is what's used for a diagnosis. Now you could go a step further and take some sort of biopsy and do some more rigorous testing of whether it's cancerous or not. And so for this data set, they also did that. And so that means that we can use these various metrics that were computed from what you saw in the microscope to whether you actually have cancer or not. So that is the task. So what's pretty different about this task from the ones that we've seen until now is that there's only two outcomes for the target or for the label. It's either benign or malignant. Whereas until now, we've been focusing on targets that are real valued. They can take on, many different values. And in this case, like it's you could say it's categorical because it doesn't really make sense to come up with a prediction that is, you have to say this thing is either benign or malignant. There's nothing in between. So that's the data set. For this particular data set, for some reason they use the numbers 2 and 4 to represent benign and malignant, but that's not really important. We can use any numbers we want as long as they're different because it's just two classes or two categories. Okay, so there's another slight complication with the feature data in this data set. The feature data are integers from 1 through 10. So if we want to plot a scatter plot, we're in trouble because all the values get superimposed on top of each other at exactly the same locations. So here you can see we're plotting one feature on the horizontal axis, another feature on the vertical axis, and we're trying to visualize the two categories, benign or malignant, using different colors. But we have to do one extra thing here. Because the samples end up falling on top of one another, what we're going to do is we're going to make a dot whose size increases the more samples that are at that location. So this big green dot here, there's actually a small red one inside, but this big green dot means that for that combination of features, almost all the samples were benign. On the other hand, over here, you have lots of samples were malignant, and so that's the data set. So in order to plot this, we had to do a bit of extra work, but it can be done. Okay, so given this data, how would you propose to classify whether we have, given a combination of these, how would you propose to classify whether it's benign or malignant, just visually? So let me see. I'll ask, is Joe Lippis here?
Yeah.
Okay.
So the colors are more close together, and you say that you usually like each is.
Okay, but let's say I gave you a specific, like I gave you 2 and 2. Like, how would you decide? You would.
I guess just by the size of the actual points too.
Okay.
Those are more green, big ones. I'd say.
Okay. So So it sounds like you're saying that wherever you look, you can kind of see whether there's more red or green, and then you could actually make like some sort of partition. Maybe it would go like this, where anything below that curve has more green than red, anything above has more red than green, right? So we've kind of uncovered this one principle that's a little different from anything we've done in regression, which is that we can make what are called decision regions. So we can say that this region of the feature space would give us one answer, and this region, the feature space, would give us a different answer because there's a finite number of answers or labels we're trying to predict. Okay, so yeah, and that's kind of what we're going to do. It's going to be a matter of how we're going to design that particular curve to partition the feature space. Okay, any questions on anything with the setup? Okay, so all right, so we can talk about this mathematically. So let's say we're given a training data set of XY pairs. As before, our xi vectors are d-dimensional, but now what's a little different is that our targets, or I'll often call them labels, now that we're working with classification, these labels are binary. It's a little bit more convenient for us to use the numbers 1 and -1, although it's not strictly necessary. Like you could also use 0 or 1, or you could use 2 or 4 like in the demo. It doesn't really matter, but just mathematically we're going to focus on 1 and -1 to be more consistent. Okay, so that's what we're given as training data. And then the problem we're trying to solve is if someone gives us a test vector x with no subscript I, and then there's some true label that we don't know, y, we're going to try to predict what that is. These two different possibilities for y are called classes, and so this problem is called classification. In particular, now we're only looking at binary classification. There's just two possibilities. Later we'll look at non-binary classification where there's possibly more than two. Okay, so examples we've already seen, are these cells cancers or not? Another one on the right, maybe you're given this image and you're asked, is this a weed or a crop? So the important thing is that there's only, what you're trying to predict is one of two things. So we can think about designing some sort of function. We'll call it a classifier. This classifier is a function that takes in our features x, our feature vector, and returns a single binary label, in this case either 1 or -1. So this is the function that we want to design. And you could say, well, what is our objective, loosely speaking? So RSS doesn't make as much sense as it did for regression because, RSS is like we want to get close to the target. So now, the target is either 1 or -1. So sometimes we're exactly going to be hitting the target. Maybe if let's say the true target is 1. So sometimes we're going to be hitting it exactly, so there's no error. The other time we're going to be very far from it. And if you think about like how that RSS would manifest, it would basically just be a matter of saying how often are you not hitting the target. And if that happens with 20% probability, then that directly will determine your RSS. It's just going to be the difference between these two values squared. So it's really about the probability that we're making the right answer or not, rather than something like RSS. So that's our goal, is to hit the target with high probability. Okay. And then as we said before, we can think of F as defined by decision regions. So on the right, we have a picture of one decision region, which is anything to the left of this curve. The other decision region is anything to the right. And in terms of the math, we could say this region is the set of all x vectors such that our classifier returns -1. This is the region associated with -1. And then the region associated with 1 is the set of all vectors for which the classifier returns 1. So one region would be this, the other region would be this. All right. Any questions on this? Making sense? Okay. All right, so we're going to spend a lot of our time focusing on a particular way of doing this classification that is called binary linear classification, in part because it's simple, but also because it has several other advantages that I'll talk about in a moment. But this is going to be basically a two-stage procedure. The first stage is to construct or compute what's called a score, sometimes called a discriminant. And so this has, we're going to call it Z, and it's going to have an equation that looks just like what we saw for linear regression, except all I'm going to do is change some of the variables just a little bit. So here we have an intercept term, B, similar to our beta 0 before, and here we have some slope terms, which I'm now calling WJ instead of beta J. And I'm making this notational change just because when you look at the literature for classification, these are the most commonly used variables, so I just wanted to be consistent with that. But you can think of this exactly as the same as beta 0 and beta J as before. Mathematically, it's identical. So this is the first stage, is to compute this Z. Now you can see this Z is not going to be binary, it's just going to be a real number. So the second stage is to threshold that score to make it binary. So if Z is greater or equal to 0, we will set our final classifier output y hat as 1. If, on the other hand, it is less than 0, we'll report -1. Okay, so that's a two-stage procedure. First, you compute the score, real number. Second, you threshold that score to get a binary number. Okay, so this is called linear classification because it's linear two different ways. It is linear Z. Z is a linear function of the coefficients, B and W, J, but it's also a linear function of the features X, right? So it's linear in both. And there's sort of different consequences to those two different linearities. In any case, our goal is going to learn the weights and intercept from the training data. And then once we have them, we can just apply this procedure to the test data to get our test label. Okay, so we're going to try to understand about how to do this, and in particular how to train it, because that's going to be just a little bit different than how we trained the linear regression that we saw previously. All right. Any questions on this approach? Is it making sense so far? Yes.
Does this give like any certainty to the predictions? Because like, if something is like z equals 0.01, is that just treated as equally as z is equal to a trillion?
Yeah, at the moment, that is what we're saying. We're not really making any probabilistic interpretations. However, when we look at a good design, we're going to have to come back to that idea of probabilities, probabilistic modeling, and that will be the path we eventually take. Just a little bit later today. Okay, great. So, any other questions? Okay, so one of the interpretations of this visually is that there's a particular value of z where you're right on the boundary between those two outcomes, right? In particular, when z is 0. And even though we assigned z equals 0 to the outcome y hat is 1, it's really sort of arbitrary. You will find that in practice, you probably almost never get z exactly equal to 0. It's usually just a little bit, at least a little bit different. In any case, here we assigned it to 0. But that's really the point that's right on the boundary where we really don't have any certainty of what y hat should be. And so we call that set of x values the decision boundary. And in particular, we can write that in terms of the math. That's when the score exactly equals 0. And we know that the score has this equation. So that means essentially that boundary is described by the set of points that cause this expression here to equal 0. Okay. And that boundary is illustrated on the right by that dark line, at least for a particular classifier that we designed. So, for this data set where the red class is here, the blue class is here, this seems like a pretty good choice for that boundary. It perfectly separates perfectly separates the training data into those two regions. Even for this one, when it's not as easy to do that, it looks like it's doing a pretty good job where it's not making a mistake on too many of the red samples or too many of the blue samples. Okay. So this decision boundary takes the form in this. This is a picture of d equals 2 features. This takes the form of a line. What would you think happen if we had 3 features? So let me see, is Alex Miller here? Yes, yeah. So like, if I had 3 features, a little bit harder to visualize, but imagine I have 3 features. The decision boundary manifests as what? So it's still going to be kind of linear. It's going to have that linear flavor to it. So imagine that you have 2 clumps of dots, like 2 clouds. And so you want to split them in half, like split the space in half. What's going to do that for you? Not a line, but since we're working at 3D, it's a plane, right? Yeah, it's a 2D plane. So generally speaking, when we're in a d-dimensional space, this decision boundary is going to be d minus 1 dimensional, a plane of d minus 1 dimensional. So for 3-dimensional feature space, there's going to be a 2-dimensional plane, cutting it into 2 halves, splitting it linearly. If you're in 4-dimensional space, then there's a 3-dimensional plane. As humans, we can't really visualize that anymore, but that is what's happening. And the intuitions, all the geometry is basically the same. So when you understand this in 2 and 3 dimensions, you essentially understand it in any finite dimension. So that's kind of nice. Okay, so that's this hyperplane. And we call it hyperplane because, a plane would be the 2-dimensional case, and a hyperplane is just like a plane, but generalized to a higher dimension. Okay, so that is what's separating our decision regions. That's what's splitting us such that on one side of the hyperplane, y hat is one value. On the other side of the hyperplane, y hat is the other value. Okay. So the important thing is this boundary itself is linear in x. So that's one of the important sort of intuitions from one outcome of doing this. And the linearity of the boundary is correct. It comes directly from this. So it's like if you think which values of x cause that to happen, that is going to be true along lines, basically lines or planes in the feature space. Okay, is this making sense so far? Okay, so this approach that we've described works well when the data is what we call linearly separable. So linearly separable just means that the training data is such that you can split it cleanly according to its class using one of these planes. So like in this picture, all the square points are here, all the round points are here, and it's possible to come up with a line that perfectly separates it. And in fact, if you can come up with one line, the red one, you can probably come up with a different one, like the blue one. It's usually not unique. It's usually you have a bunch of freedom in terms of how you come up with that line, that boundary. Okay, so that's So that's the idea behind linear separability. It's sort of a primitive idea because in practice, it rarely happens. In practice, maybe you have something more like this. There's really no way to cleanly separate this into red and blue. Any kind of line you come up with is going to be some trade-off between, making some errors in the blue here, some errors in the red here. So that's an important comment. However, there are going to be some data sets where you can approximately split things in this clean manner linearly. And there's other cases where if you're clever, you can come up with some nonlinear transformations of your features and define new features based on those transformations. And in that new feature space, you can separate the data linearly. So that ends up being essentially how all these modern methods in machine learning, like deep neural networks, that's how they work. As we'll talk about later, you can think of all the early processing stages as these sophisticated nonlinear transformations of your features that present the final stage, which is just a linear classifier like we're describing here. They present it with these new features that are linearly separable or very nearly so, and then the classifier gets great performance. Okay? Even though in the original features space, it looked extremely, looked like it was impossible to classify. Okay, so that's sort of the power of this linear method, is that it can incorporate nonlinear feature transformations, and then we can still use all the equations that we'll derive, all the design, we can apply it after those transformations are done. Okay, so that's one of the reasons we're doing it. Another reason is, as a linear scheme, it's just pretty simple, so we have a chance of understanding what's happening. And then another reason is, as we saw in the last unit, linear methods facilitate feature selection. So if you are asking the question, which of my features is most important to making this correct prediction, and you standardize your data, you can then look at the size of the coefficients, the W's, and you can say, oh, this is a big W. That probably means that feature was very important to making this classification correctly. If a W is really small, it probably doesn't matter that much. Okay, so these are all the different reasons we might want to use linear classification. And as I mentioned before, we can think of it as a building block for much more sophisticated strategies like neural networks. Here's a picture of a data set where, in terms of the raw features, green and blue, there's really no way to linearly separate them. So if you were working with a linear classifier and this raw data set, there's no way you could get good performance, just impossible. However, if you come up with, let's say that 0 is in the middle of this circle here, if you came up with this new feature, which is square root of the first squared plus the second squared, that's essentially the radius, right? Now, in this new feature, which is just the radius from here, you can linearly separate things. If the radius is less than this amount, it's blue. If the radius is greater, it's green. Okay, so just a simple contrived example of how nonlinear processing can take a problem that's not linearly separable and make it into a problem that is linearly separable. All right. Okay, any questions on anything so far? Okay, great. So the next question, and really the most important question, is how do we fit our parameters, slopes and intercept? So one thing we could try is we could just try to reuse the tools that we developed in the last unit, which were basically least squares fitting regression. And so for that, we could just say, well, why don't I just treat the labels, the y's, as things I want to predict, like get a least squares fit to them. So for example, we know how to do that. You just stack all these labels y into a vector. You make a matrix A with 1 as the first column and then the features in the remaining columns. And then we make a vector of intercept stacked on top of the slopes, W. And we minimize that, that Euclidean norm. So that's our RSS. So we know how to do that, can definitely do that. We, just plugging in these binary targets now. Once we're done, we have to do just something a little bit different. So once we're done, we know those values, B and W. Let's call them B least squares, W least squares. Now someone gives us a new test feature vector. We compute the new score, Z. That's a real number, though, and we said that the goal of classification is to predict the binary value, return the binary value. So, okay, all we need to do then is quantize the score. If it's 0 or positive, we output 1. If it's negative, we output -1. And boom, we have a classifier. Right? We have a linear classifier. So the question is, does this use of least squares linear regression work, or does it always work? And it turns out that, yes, it works in a few cases, but in general, it doesn't work very well. So let me show you just by way of an example. And this is just a one-dimensional classification problem where we have a single scalar feature x. Here's our target y. So our target, our training data, we have a few values here at -1, a few values at +1. And so according to this two-stage approach, first we fit a linear model that returns a score. This is going to give us our z, or here I called it z hat. And then whenever z is positive, we return 1. So here I'm thresholding z and turning that to a green curve. So this is the set of x for which we got a positive z. And so I'm going to return y hat as 1 for all those values. And then you can see z is negative here, so I'm going to return -1 for all those values. And yes, this works really well, right? It's fitting our training data perfectly. It's doing exactly what we would hope for this data set, just based on human intuition, right? Everything looks great. So now let's see what happens if we just change things a tiny bit. So we're going to take this point here, and we're just going to move this to the right. So here we moved it so that instead of being like value of 9, it's a value of 20. So this is where the procedure goes wrong. So to do this least squares linear fit, as we know, what we want to do is we want to come up with a regression line that minimizes sum of squares. So when you look at the errors on the training data, those are the errors. We would be minimizing the sum of those and the sum of these. And because this last point to the right is so far to the right, if I came up with this, this original design here, you would have this massive error on the right. It would contribute hugely to your RSS, and so that wouldn't be optimal. So what happens is this whole line gets pulled down to accommodate this outlier feature here to minimize the overall RSS. Okay. However, as a result of that, when you look at what happens when we quantize this z, so this is like our z here. So whenever z is positive, which is from this value to the right, we want to assign y equals 1. Whenever z is negative, we assign -1. But here you see that it's not even fitting our training data anymore. For example, this training data sample here would be given, this value would be given a negative y instead of the positive 1. So it's just sort of not really handling this kind of imbalance in the data. So just loosely speaking, intuitively, we can describe it that way. When the data is nice and balanced, this least squares approach seems to work well. But when the data is imbalanced in that, these y equals 1 samples are spread out and these are clustered more closely, then there's some issue with what least squares is doing. And so we can trace this back to basically the choice of RSS. RSS is really not what we want to use. In fact, when you think about this point here, from the purpose of classification, it's almost like the most obvious point. The least obvious points, I think, given the data, are the points here when when we're less sure whether it's 1 or -1. As we go to the right here, according to this data set, like the further we go to the right, the more obvious it is that the point deserves a target 1. But, so this is the most obvious one, but yet that is somehow confusing least squares. So it sort of has the wrong approach altogether. It should be spending most of its time trying to figure out what's happening here, and this is the region of difficulty for classification, not over here. Okay, so that's essentially just sort of a loose, intuitive understanding of an example where least squares fails. RSS is not really what we want to minimize for our loss function. Okay, any questions on this little example here? All right, so what about our breast cancer data? So here we're extracting, again, 2 features from a breast cancer data set, size, UNIF, and MARGE. And we can, again, try the same least squares approach. If we do this, we end up getting this as the hyperplane that is separating where we're going to predict red, malignant versus green. And you can see that this is also having trouble. The green points are really down here. This is mostly red, but yet where we're putting this, it's going to predict that all those points here are green. And the issue is, again, sort of the same one we saw before in one dimension, which is that all our benign samples are kind of clustered tightly, whereas our malignant ones are sort of spread out. So we have the same imbalance, but just in 2D. So this is sort of, again, explaining what's going wrong here. And we can even be a little bit more precise about how can we translate this condition to draw that line? Well, all you need to do is really just think of this as x1 w1 plus x2 w2, and rearrange things a little bit to put x2 on the left side of the equation, and you get x2 is minus b over w2 minus w1 over w2 x2. And so once you have it in this form, you can see that the decision boundary has an intercept of minus b over w2 and has a slope of minus w1 over w2. Okay, so in case you need to do this on a homework or an exam, that's how you translate this form of the decision boundary to this form where you can easily plot it in terms of the intercept and the slope. Sorry, this is the intercept over here, and then the slope here. Okay, is everybody good with that? Does everybody see how we can draw this boundary based on these coefficient values? Okay, so all right, so again, we have another case where the feature data is imbalanced and minimizing RSS is not really working well for linear classification. Now, that's not to say that there's a problem with linear classification itself, because, if I'm just forced to draw a line, well, I could draw a pretty good linear boundary over here, and, I think this particular problem looks like we can approach it pretty well with linear classification. It's more like the way that we train the classifier is the issue, not the linear constraint of the classifier. Okay, so yes.
Should that be an x1 there?
Oh, yes, sorry, that should be an x1, thank you. X1 there. Okay, all right. Any questions on where we are? Okay, so now is maybe the more interesting part of the lecture, is how do we actually train this? And it really sort of comes down to choosing a loss function, but most of the loss functions that people come up with in machine learning have a probabilistic interpretation or maybe even a probabilistic statement. And so we saw that for the first time, I think on Friday when we started talking about maximum likelihood. And that's when we saw that this idea of least squares linear regression is actually tied to this linear Gaussian model where the noise is Gaussian. And so we had this likelihood function that was Gaussian. And when you take the log of it and simplify terms, it turns quadratic, and that's where we've got least squares from. So here, that's exactly the approach we're going to use, but we're not going to be using a Gaussianity and so on. We're going to be using a different probabilistic model that is more suited for this binary classification problem. Okay, so again, just to review, for linear classification, we have this score z, which is linear in the features x, as well as the coefficients b and w. And then once we're given z, we quantize it to get y hat, depending on the sign of z. So the whole question now is, how do we design those parameters b and w? We saw that RSS is not the way to do it. So, okay, how can we do it? So there's many, many ways to do this. The one that I would say is the most well-used, well-studied, uses a particular probabilistic model, which is one of the simplest to work with. And it looks like this. So you have the probability that the label is 1, given the score, is this fraction. In the numerator, you have e to the z, being the score, and in the denominator, you have 1 plus e to the z. So like if I tell you the score, then now you have a probabilistic model on what the label value is. So down here, you have a picture of this. So if this is the score z on the horizontal axis, on the vertical axis, we have the probability that the label is 1 given z. And you can see that, okay, when z is 0, which we know is right on that boundary of decision, we really have no idea whether y should be 1 or 1. It's 50-50. As you get z moving to the right, growing larger than 0, we're more and more confident that the label value is 1. We never get all the way to full confidence, but we start getting pretty close, already for values of z like 5 or 6. Asymptotically, as z goes to infinity, we eventually get to confidence that the label is truly 1, but it just gets closer and closer as we get there. On the other hand, if you go to negative z's, now you can see that we are more and more confident in the alternative, that z is 0, or confident that z is not equal to 1. So really that's the whole intuition behind this model here. I'll put a box around it. This is really the main equation now. It's just one choice. There's many, many other probabilistic models, equations you could plug in here. When you start to do differentiation to minimize the log likelihood and so on, this is just one of the most convenient ones to use. And in practice, it works very well. So that's sort of explains its choice. But there are certainly many others, and we will study some alternatives later in the course. Okay, so this is what we have for the probability that the label equals 1 given z. Any questions on this? Is this making sense? Sort of the idea of, it's not so different from what we had with our Gaussian noise model, because even there, if you say y equals, again, z plus Gaussian noise, like you never know truly the value of y. You just know sort of a distribution on the value of y given z. You just know it's around z, but it can be to the left or to the right because there's that noise. And there you had a Gaussian conditional probability. Now we have this other one, which is called a logistic, or sometimes a sigmoid function. Okay, that's the name of this curve. Okay, so good time to pause for questions. Is this sort of making sense? Okay, no questions at all? Everybody good with this? Okay, so we have a conditional probability here. It's also useful to say what is the probability that y is minus 1 given z. Not too hard to get it if you think about it. Can I, let's see, is Ram Saiganesh here? Yeah, what do you think? Exactly. It's 1 minus this. So it turns out that that would be 1 over 1 plus e to the z. And I think what you use there is the idea that, well, there's only 2 possibilities for y. It's either 1 or minus 1. So for any given z, the probability that it takes on, y equals minus 1 or y equals 1, that has to be equal to 1. They have to sum up to be equal to 1. And that is exactly what we need. So for any z, those numbers have to sum up to 1. And yes, if you add these 2 things together, you can clearly see that that's 1 no matter what z is. And so you could, if you wanted, you could imagine plotting that here would be just the mirror image of this. That would be the probability of y is minus 1 given z. Okay, so that's the whole idea behind this probabilistic model. The very last thing is sometimes this expression, which has 2 exponentials in it, is simplified by multiplying the top and bottom by e to the minus z, in which case you get 1 over 1 plus e to the minus z. That is sometimes a little bit easier to work with. There's a single exponential, so that's just another form of the same curve. Okay, so that is basically, that's the main idea. That's what we're going to use to train our classifier. We're gonna somehow use this, but we're going to do it with maximum likelihood because that is the way that we can take this probabilistic formulation and figure out how to come up with the values of b and w that that maximize the likelihood, that make this the most probable model. Or most likely model. Okay. All right, any questions before we move on? Okay, so we'd like to get a little bit more intuition because here, notice that we are writing this model in terms of z. Z is the output of this part. We really care about how does it depend on x, right? Because then we can actually understand how b and w affect things. Okay, so how does this behave? That's the next question. So let's do this in small steps. So just to keep things simple, imagine that I only have a scalar feature, and furthermore, imagine that I set the intercept to 0. So in this case, my model is simply that z is a slope coefficient w times x. Okay, so now the question is, what is the effect of w on the shape of the curves, in particular, probability of y equals 1 given x? Okay, so obviously if w is equal to 1, we have exactly the curve on the previous page, which is illustrated here. So this is our logistic function that we saw on the previous page. So now imagine that I make w smaller than 1. So the way I think about this is if w is smaller than 1, it takes a bigger change in x to get the same z. So what that means is that this gets spread out. You have to make x bigger to get the same height. So that's what happens if you make w small. This expands, but in this case, it's still centered in the same spot. So when x is 0, you get 0.5. On the other hand, if w is made larger than 1, now it doesn't take as much of a change in x to get the same z. So now you get a much more sharper transition around the point 0. Okay. And further, if you make w negative, then it actually flips the orientation of this curve. So now, as x gets larger, you can see that actually the probability of y equals 1 decreases rather than increases. Okay. So these are just, helps us understand now the role of the coefficient w when viewed in isolation. So it changes how the logistic is stretched, and it could possibly flip it as well. All right. Okay, so sharpness, increasing versus decreasing. Okay, any questions on that? All right. So now let's bring in W. Until now we've set W to, let's bring in B, set it to 0. So for general B, the easiest way to see what's happening, so remember we have Z is B plus W times X. It's easiest to pull the W out, and then inside we're going to have B over W plus X. And now you can see that the role of this term, B plus W, is actually what's going to shift the transition point. So now, like, I have to make X equal to minus B over W to get Z equals 0. So essentially, the transition, instead of being centered at X equals 0, is now centered at X equals minus B over W. Okay, so it shifts the curve left or right by minus B over W. Okay, so that's essentially when you are adjusting these parameters B and W, you're shifting and stretching that logistic curve. So we have a bunch of data and we want to shift it and stretch it in just the right way that it fits our data best. And that's what we're going to do with maximum likelihood. Okay, any questions on anything so far? Okay. All right, so maximum likelihood, we talked about this the end of last week, last Friday. So let's just review briefly what we do. So we define a likelihood function, which tells us the probability of a set of samples y, we are assuming n samples, y1 through yn, given a set of features, x, and some model parameters, in this case, B and W. And then what we do is we say, let's find the model parameters that maximize this likelihood, where again, y and x are fixed because we know them from our data, so we're just adjusting these until the value of this entire probability is maximized. That's what we do in maximum likelihood. We said that actually a lot of times the probability function involves exponentials, and so when you actually start deriving things, it helps put in a log there. And even a little bit more, we can turn this into a minimization problem, which is a little more common if we put a negative in front of that log. Okay, so, and we did this for linear regression. We said, okay, let's look at the specific case where y equals A times beta plus Gaussian noise with variance sigma squared. That means that the overall likelihood is Gaussian with this mean and this covariance matrix. And then we took the negative log of that, and we found that that was equal to this scaled Euclidean norm squared plus a constant in beta. And then finally we said, okay, if our objective is to minimize this negative log likelihood, we can do that simply by minimizing this squared norm. And we can also then recognize, well, this squared norm is nothing more than the RSS that we talked about back in Unit 2. So this sort of connects us back to least squares fitting. That is exactly what happens when we have this linear Gaussian model and we apply maximum likelihood estimation. Okay, so the only difference now is we again use the same procedure, but we just use a different likelihood. In particular, we use this likelihood that we introduced over here, the logistic likelihood. So is that sort of making sense, how we're approaching this problem? Okay. And essentially, as we go through the semester, we're going to do this over and over again. What will keep changing is our choice of the likelihood, but the maximum likelihood procedure will just, that's going to be our go-to procedure. Okay. All right, so we had to do a little derivation here. It's really not bad. There's just one step that's a little tricky. But this is what we start with. So we said that, okay, if I look at a single sample, single training sample yi, the way that I can write the probability as well, we have an expression that says the probability that yi equals 1, given my features and given my parameters, we know it takes on this thing here from the logistic sigmoid. And zi, that's the ith score, that takes on this value. So here we have our ith training feature vector. We have our parameters b and w. And so this is what we get in the case that y equals 1. Is everybody with me there? Okay, now, what's inconvenient about this logistic regression framework is that when we write down the expression for yi equals -1, we actually get a completely different expression. It's like we don't have a common expression that covers both cases. And so that complicates our lives a little bit when we do our derivation. So let's say we start out like this. So we're looking for this generic likelihood that holds in all cases, that relates the probability of y, or that explains the probability of y given x and our parameters. Okay, so the first step we always take in maximum likelihood is we assume that all these yi's are independent of each other if we condition on the features and the parameters. So that allows us to write this joint probability as a product of individual probabilities, sometimes called marginal probabilities. So that's always the first step. Next step is we can take the negative log, and that turns this product into a sum, a negative sum, and here we have the log of our PYI. But here's where it gets tricky because we don't have an expression for PYI that covers both cases when yi equals 1 and -1 for logistic regression because we actually have two different expressions. So we can actually fix this with a little trick that looks a lot like one-hot coding that we saw with features, but in some sense you could say we're one-hot coding the targets now. Another way to think about it is to introduce a switching variable. So we're going to stick in these two variables here, and we're going to exploit here the fact that yi takes on one of two values. It's either 1 or -1. Okay, so when yi equals 1, you can see that this first term here turns into 1, right? And the second term turns into 0. So when y equals 1, that means you're using this, but you're ignoring this expression. And we know what this is. That's just this expression above. So now in all the cases where y equals -1, so in that case, you can see that this turns into 0, which kills this part, and this part turns into 1. And as a result, we switch in this. So essentially we introduce these two variables here that are switching in or out these terms depending on whether you have yi equals 1 or -1. And now that we have that switching going on, we can simply plug in the appropriate expression for here, or there. Okay, so that's really the main trick here. Beyond that, the rest is just simple algebra. Is that trick sort of making sense? Okay, so the only thing is now if I told you that the labels were not 1 and -1, but 0 and 1, you could do something very similar. You would just need to change the details of how you define these so that the first one is 0 or 1, the second one is 1 or 0, just depending on the two values of y that you're working with. Okay. But you can always do it. You can always come up with some assignment that works. Okay, so is everybody good with this here? Yeah? Making sense? All right, so the rest is pretty straightforward. We just need to look at the log of this. So you can see that's going to give us the log of the numerator. The log cancels the exponent, just gives us zi, minus the log of the denominator. There's really no way to simplify that. 1 plus e to the z log of that. You just can't simplify it, so that's what we're left with. Then for this other term, want log of this. So log of the numerator, log of 1 is 0. So we get 0. And then again, log of the denominator minus log of 1 plus e to the power z. And then we just distribute terms a little bit. Just distribute this through. And finally, you get a couple terms here and here that will cancel out. And these two terms live on. And this is what you get. This can't really be simplified further. This is the negative log likelihood. This is the thing that we want to minimize. Okay, so that's, okay, and again, this is written in terms of the zi's, and here the zi's are written in terms of the b's and w's, so it's a little bit complicated, but this is how we have to do it. Okay, so that's really it for the derivation. Is everybody good with this? Okay, just to summarize it. Oh, actually, no. So yeah, let me just do the summary. So essentially, this is what we just derived. So if your targets are 1 and -1, want to find the b and the w that minimize this sum here. This is written in terms of the zi's, and the zi's are written in terms of the b's and the w's. On the other hand, if your data is 0, 1, which is another very common form that it shows up in, and you come up with slightly different switching variables, you instead get this expression. So the only difference here is that instead of that, you have this. Okay, so this is essentially, this is the optimization problem that we need to solve for logistic regression. This is unfortunately not one that we can solve on paper, but it is something that we can solve numerically. And it turns out that actually this is what we call convex, and so we can definitely optimize it with a numerical algorithm. That's not an issue. And then in practice, scikit-learn does this for us. Okay, so we're out of time for today, but next time we'll see that this actually does work perfectly on our simple data set. And yeah, this is why it's a very well-used method. So I'll see you guys on Wednesday. Have a good one.